Hello students, this video is about the oxidation states and the trends of the oxidation states in the periodic table. So let's start with the definition. The oxidation number of an atom in a compound is the charge with the sign which it would carry in the compound. I repeat, the oxidation number, it is the charge on an atom which it would carry in a compound. For example, this is sodium chloride. This is the common table salt which you all should be familiar with, and it's an ionic compound. In ionic compound, the oxidation states they are determined on the basis of the number of electrons gained or the number of electrons lost. In this case, the oxidation state of sodium is +1 and of chlorine is -1. On the other hand, this is carbon tetrachloride, CCl4, and it is a covalent compound and it is formed by the sharing of electrons. In this case, the oxidation states it is defined on the basis of the difference in the relative electronegativities. And students, electronegativity, it's the chemical property that describes the tendency of an atom to attract shared pair of electrons towards itself. In this case, the oxidation state of carbon is +4 and of chlorine is -1. Now chlorine, bromine, oxygen and hydrogen, Cl2, Br2, O2, H2, they are in the free state. The free state, it is the uncombined elemental atoms, whether they are lone or diatomic or polyatomic, and the oxidation state shown by these is 0. Now you can see that this is sodium, it has 11 atomic number and its electronic configuration is 281, and chlorine, it has electronic configuration 287. The outermost shell has 1 electron, and in chlorine the outermost shell has 7 electron. So sodium loses 1 electron and form +1 oxidation state, and chlorine, it gains 1 electron to complete its octet and have -1 oxidation state. Now this cation and this anion, they have strong force of electrostatic attraction and they form a strong ionic bond. On the other hand, this is carbon in the ground state and this is carbon in the excited state. Sorry for the inconvenience. This is 2s, 2px, 2py and 2pz, just like here you can see. Now one electron from 2s orbital, it jumps into the 2pz orbital and form 4 unpaired electrons. These get paired with 4 chlorine atoms and form CCl4 compound, which is a covalent compound. Now you know very well that chlorine is a halogen and it is highly electronegative as compared to carbon. So all the chlorine atoms in carbon tetrachloride will have -1 oxidation state and carbon will be having +4 oxidation state. Now students, let's discuss something about the trends of oxidation states across the period, that is from left to right. The oxidation state of a typical element is directly or indirectly related to the group number to which the element belongs in the periodic table. This is the subgroup A. So group 1A to group 4A, the elements of group 1A to 4A, that is alkali metals and carbon family, they have the same oxidation states as their group numbers. For example, boron, aluminium and gallium also, they belong to group 3A and has +3 oxidation state. So for the elements of these groups, the oxidation state is same as the number of electrons present in the valence shell of the elements. For group 5A, the elements in this group, the oxidation states are either the number of electrons present in the valence shell, which is the same as the group number, or the number of vacancies available in these shells. For example, nitrogen, phosphorus, arsenic and antimony, they show -3 as well as +5 oxidation states frequently. Now here you can see that this is boron, 1s2, 2s2 and 2p1, 2 inner electrons and 3 outer electrons. These 3 electrons, they can be lost and boron form +3 oxidation state. On the other hand, this is nitrogen, 1s2, 2s2 and 2p3. You can see that 3 vacancies are available, 1, 2 and 3. So it can have -3 oxidation state, or you can see that it has 2 inner electrons and 5 outer electrons. 5 is the group number of nitrogen, 5A. Nitrogen belongs to 5A. So it can have +5 oxidation state as well. Now for group 6A, which is the oxygen family, oxygen, selenium, oxygen, sulfur, selenium, tellurium, polonium. They show similar behavior as of group 5A. As in sulfuric acid H2SO4, the oxidation state of sulfur is positive 6, and in H2S, which is hydrogen sulfide, it is minus 2, which is the number of vacancies in its outermost shell. For group 7A, which is the halogen family, the fluorine, chlorine, bromine, iodine, and acetylene, the oxidation state, it is always minus 1, which is the number of vacancies in the outermost shell. And for group 8A, which is the inert gases, the oxidation state is 0. For 8A, the oxidation state is 0. It is also called as zero group elements. Usually they show zero oxidation state because there is no vacancy available in their outermost shell. Now you can see in sulfur, there are 2 inner electrons. In the next shell, there are 8 electrons. And in the outermost shell, there are 6 electrons. Now you can see there are 2 vacancies available. So it can have minus 2 oxidation state or 6 electrons. So it can have positive 6 oxidation state, which is the same as that of the group number 6A. Sulfur belongs to the 6A group. Now chlorine, you can see that there are 7 electrons, 7 valence electrons. So it has only one vacancy available and it can have minus 1 oxidation state. Now the transition elements, which are the subgroup B, they usually show more than one oxidation states. And these elements, they also show the oxidation states which is equal to the group number, as it can be seen for copper 1, zinc 2, chromium 6 and manganese 6, like here. You can see that this is the 1B group, coinage metal, copper, silver, aurum, Au is gold, and this is 2B, zinc, cadmium and mercury. This is the third group, 4th, 5th, 6th, so on. So copper will have positive 1 oxidation state, vanadium will have positive 5 oxidation state, manganese positive 7. So they show the same oxidation state which is equal to the group number. These elements usually show more than one oxidation state in the compounds because they have greater number of valence electrons available in the partly filled d orbitals. So you can see that this is the first series of the transition element. This is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. It has incomplete d orbitals and they are in the process of completion. So that is why they show different variable oxidation states. And that is why they are also known as d block elements. Now you can see that down the group, the trend is that due to the same outermost shell electronic configuration, the elements of the same group, they have the same oxidation state. Because they are in the same group, all the elements are in the same group, so they have the same oxidation state. So there is no general trend of oxidation state in a group. I hope this video was helpful. If you like this video, please like, share, comment and subscribe. Thanks for watching. Wish you all the best.